All right, I think we have our first participants. Very exciting.
Yeah.
It's one thing I've noticed is that people do not come as early to online classes as to regular classes, which you could take as a bad thing, or you could take to mean that that people are saving time on travel.
Yeah.
So, you could think of it as a good thing. It just, it gets a little lonely is all. That's all I'm saying. Can everyone see my screen?
Yeah.
Okay, excellent. Then I think we are pretty much good to go. So as the minute hand ticks over the hour, we'll be starting up. So before I begin, does anyone have any, and while we're waiting for things to start, does anyone have any final questions to clarify or ask about? Okay. Well, so today is going to be, and I've noticed that there are fewer people than expected. Hopefully they'll join in a few minutes, but I'll kind of waste some time here. Today's going to be a little bit different than what we've done in lectures so far. And that's due to a suggestion made by Abhishek, which is, because of this coronavirus thing, we're not doing assignment 5. And what I had intended y'all to do for assignment 5 was to use a tool called the checker framework. And because of the coronavirus, we've had to change the plan a little bit. So instead of assigning you the checker framework, today I'm going to be doing a demo of the checker framework. So you can see I've already put up links to the code that I'll be using if you want to look anything up in the code while I'm working. And that's the code that I have on my machine. And of course, you'll, like other videos, this one is recorded to YouTube and so on. So we'll be doing today a demo of the checker framework. And there's one more change to the schedule I wanted to highlight, which is that I've decided to also create a demo for this tool called Lean, which is a dependently typed theorem prover of the sort that we'll be talking about for the 3 lectures after that. And I've taken that demo, I've moved it to be Thursday. The idea being that you'll have, a little bit of actual practical sort of examples of how you might use Lean to prove theorems and to verify code, so that you can sort of move that forward before we actually discuss sort of the theory of how that tool works. So to sum sort of all of that up, today and Thursday are demo week. Today we'll be doing a demo of this tool called the checker framework. And in particular, I'm going to be telling you how to use the checker framework to verify programs in Java using the abstract interpretation technique that we've been discussing in the previous lecture. So unlike my usual lectures, there won't be slides because I'll be, writing code in a text editor and demonstrating different things the checker framework can do. But like a normal lecturer, please ask questions in the usual way, which is the raise hand icon in the participants panel of Zoom, and I'll call on you as normal. So any questions about how we're gonna do this? Excellent. Well, I'll start by introducing the checker framework. The checker framework is a abstract interpretation framework. So it builds on top of the Java compiler. And in particular, it intercedes in the Java compiler. And after the compiler has finished type checking your Java program, but before it has begun compiling it, it runs an abstract interpretation pass. And in that pass, it can flag errors, tell you about problems in your code, and basically verify facts about it, much the same way that we've discussed in the previous week. So it has this idea of specific conditions that it can describe about program variables and program values. And it has techniques for flowing those through the program using a OR operation on those conditions, transfer functions and refinement functions, as we've discussed. So the main innovation of the checker framework is that it applies directly to Java code. It plugs into the compiler, and you can run this on Java code that you have. And in fact, it's being used by large companies. If you just look in the manual, you'll see references to checkers developed by, for example, Amazon, which uses the checker framework fairly heavily, as well as other tools. Can everyone hear me fine, by the way? Hello?
Yeah, we can hear you.
Okay, great. The chat was just slow to get here. Cool. So instead of giving you sort of a deep and complicated introduction to the checker framework, let me just show you some code using the checker framework. So what I've got open here is Emacs, and I have developed, I'm planning to demo to you some number of different tools using the checker framework. So some code using the checker framework. So the way I have this set up, here is a Java file. I've called it nulltest.java. And if you're not too familiar with Java, what's going on here is this is the main sort of code. It has to reside in a class, and I'll be writing code inside this test method. The rest of this stuff is defining packages that it has to import, some Java stuff, and this is actually nonsense built into Emacs that allows me to tell it that I want it to run the checker framework in the background every time I save. So let me start by telling you about the nullness checker built into the checker framework. The way it works is that if I have some kind of object in Java, that object can either be some actual value, like this new object I just allocated, or it could be the value null. And null in Java is sort of the analog of the null pointer. So in Java, you can run into problems because you expect to have some kind of valid object of some type, and instead you have the value null. So the checker framework provides what's called a nullness checker, which checks or attempts to check whether or not various objects are null. And the way you invoke the checker framework, the way you, let me check that it's running in the background. Yeah, the way that you run the checker framework is by executing the Java compiler. So that's the Java C right here, and telling it that you want it to use a processor here to process the file before it compiles it. And here, the reason that I've called Java with the nullness processor, with the nullness processor is precisely because I want to check for null values. So right now it's running and it's not doing anything, and that's it's not flagging any errors, and that's because by default it sort of lets Java code be. But if I want to invoke the checker framework, I use these things called annotations. And the annotation here, not null, is something that is provided by the checker framework. In particular, I've imported it here from the list of qualifiers. That's what I've been calling conditions in the nullness package. And you can see in the bottom right of my screen, if you can see it. Oh. Ugh. I'm sorry, it seems to have some sort of annoying Java problem. Might be some technical difficulties here. Huh. Well, I guess this is as good a time as any to introduce the other thing I'll be using in this demo, which is the Java, the checker framework manual. And I want to point out that if you want to look at it, you can find it here, checkerframework.org/manual. I sort of thought that I had this stuff correctly, but I guess not. Oh, it's called non-null. Okay. So in Java, you can use these things called annotations. And these annotations are allowed to be either a symbol like this or some sort of call of what looks like a method. In fact, this is instantiating a class in the background. So what I've done here is I've annotated this object to be non-null, and this causes the checker framework to flag an error. The error it says is that the types are incompatible. It says that my apologies. It says that the types here are incompatible, and in particular, what is incompatible is that we have what is called null, and we are trying to store it into something that is not non-null, and naturally null is not non-null. So it flags an error here. Whereas if I went with a nullable value, which is allowed to be null, then I would not have a problem. Now that's just for assigning to objects, but the checker framework provides this overall analysis that applies this null or not null status as you go through the code. So I might call a method on O, and if I do so in a moment or two, the checker framework flags an error. And in particular, the error it flags here is that this is a dereference of a possibly null reference O. And that's because I've declared O here as nullable. In fact, O is definitely null, so it's a good reason to flag an error. Furthermore, the checkout framework provides the sort of refinement technique that I talked about last Tuesday, which is the ability to make use of the results of a comparison to further understand the various values in play. So in particular, I can test whether O is equal to null and only call toString if it is not equal to null. And now you can see that that error has gone away because this comparison with null has allowed, in the else case where the comparison is false, the checker framework is refining the type of O from nullable to non-null. Refining the type to non-null, it allows this assignment, it allows this call because in this branch of the condition that is valid. Whereas if I tried to do either of these things in the true branch, it would raise an error because if O is equal to null, then an assignment to non-null is invalid. So this is sort of the general scheme of how the checker framework works. And I'm going to be using this as an example to explore some real world usage of abstract interpretation. I'd like to write some code, show you some additional tweaks and interesting things that have to be added to this lattice to make it work, to make it useful for real Java code. But let me first pause for questions about the sort of general scheme here. Actually, before I continue, who here has done programming in Java? You could do the raise hands thing. I expect it's most of you. Okay, so a majority, but not the whole class. Hao Chen asks, does the notation, this thing is called an annotation, does the annotation have to be on the same line? It does not. So the checker framework plugs into the Java compiler itself. And so all of the parsing of Java code is done by the Java compiler itself. And annotations were added, I think, in Java 8 as a standard part of Java. So all of the parsing rules are pretty much what you'd expect them. You can add new lines just like you can anywhere else in Java. Obviously, you need to do the semicolon stuff correctly, and it'll work as you expect. Any other questions? And again, if you've got a question, just do the raise hand thing, and I'll call on you. Yeah, Pranav.
So this notation is provided by this non-null notation is provided by the Java or like by the checker framework?
Okay, yeah, so let me explain a little bit how this annotation stuff works internally. If we go to, I'm probably not going to find an example of the Java grammar online, but the Java compiler itself allows this syntax. And in particular, the way this syntax works is that you write an @, then you write the name of a class, or alternatively, the name of a class and then some expressions in parentheses. And you can put that before any type definition. The syntax actually is a little more complicated than that. You can stick annotations on methods. You can also do some, if you want, for example, and you can imagine there are some complicated questions about like, what's the difference between an array of not null objects and a not null array of objects? That all stuff is settled by the Java compiler. This name, though, nullable, is actually imported here from this import statement, where I write org.checkerframework.checker.nullness.qual.star. The star here actually is import of nullable and non-null. So these are two classes defined in the checker framework package. And when I write the @ of nullable here, what I'm really writing is org.checkerframework.checker.nullness.qual.nullable. Java is looking up this big type name in its class path, with it, which is some Java thing that if you've done Java, you know about, and otherwise really don't think about it. It's looking that up. It's instantiating that class at compile time. And then the checker framework, because I am invoking this processor code here, I am actually instructing the Java compiler to additionally look up a class called nullness.nullnessChecker. And that class at compile time will use the abstract syntax tree parsed by the Java compiler, and also all of these instantiated objects for the annotations to do whatever kind of analysis it needs. And at the end of this lecture, I'll walk through a checker framework checker that I've written. We'll add some features to it, and hopefully that'll give you even more insight into how this works. But the basic upshot is that the syntax comes from Java, but this nullable class that's defined by the checker framework. And the checker framework actually defines like a bunch of different checkers, each of which has multiple qualifiers inside them. So, you know, there's like dozens of things here. Hope that answers your question, or tell me if it doesn't.
Yep.
Okay. Other questions? Okay, cool. So what you've seen here is some basic features of the checker framework. We've got the ability to create annotations on values. You've seen how some basic analysis is done, and you've also seen how refinements and such are done as well. Now, one of the big values of having the checker framework is that it handles a lot of sort of generic stuff that would come up in any analysis. For example, you might want to call a method inside your code. And when you call a method, that method has some kind of precondition and some kind of postcondition, like we've seen in Daphne. Now, when we talk about abstract interpretation, those preconditions and postconditions have to come from that selected set of conditions. So here we have a method that expects an object input, and that object input has to be not null, and produces a possibly null output. In fact, it always produces an exactly null output, but that's sort of irrelevant to the checker framework. So what I've done here is I have a method, and I've annotated both its input argument to be a not null object, and its output argument to be a nullable object. So as you might expect, it should be impossible to call this method on the value O. And as you can see in the bottom right here, I get this incompatible types in argument error. And that error tells us that I am calling method with a nullable object, but nullable is in fact a is not a subclass, is not weaker than, sorry, is not stronger than non-null. Kelvin?
So how it looks here, are these pretty much just all refinements of the different types, or is that kind of a bad way to look at it?
You can think of it as a refinement of different types for now. But one of the things that we will look at shortly, if you can see my file picker on the bottom left, is a thing called lock test. I'll leave that mysterious for now. But one of the things that the checker framework supports is these sorts of relational lattices, which I talked a little bit about on Tuesday. And that's a condition constraining not just a single value, but pairs of values. So you can think of, you know, when you talk about valid index for an array, that's already talking about not just a refinement of that integer, but a refinement that depends on some other value, namely the length of the array. And when we talk about the lock checker, we'll be talking about this idea that a value is guarded by a lock, namely you need to acquire the lock before reading it. And there we won't be restricting the set of values of that object at all. We'll instead be defining some kind of protocol about how you can use it. So, you know, for the nullable not null, it's definitely a refinement, like literally not equal null or not. But as we go further, I hope to show you that there's a lot of cool stuff you can do with this abstract interpretation framework that's not just refinement based. Matthew?
If you remove the annotation from the definition of O, will it still?
It will. And the reason for that is because null, which is a literal constant in Java, is itself, you can say, annotated as nullable.
If it was made just a single object, would it also? So
Right. So if this was made new object, then the inferred annotation for O would be non-null. So here, this is actually a non-null object O. Because I'm assigning it to a new object. Whereas if I did null, this would be nullable object O. And that would cause an error lower down. There we go. Sorry, it takes a few seconds for the actual type checker to run. That's why you see the red squiggly arrows show up back and forth. So the upshot here is that even when you don't write one of these annotations, the checker framework is doing something in the background to figure out what types it could have. In some sense, you can think about an annotation always existing, and that's because, like the way we introduced it in class, there has to be some kind of unknown value of each lattice that can apply to anything at all. And so the checker framework is always going to have some kind of annotation on every value, at least for the types that are interesting to an analysis. Nullness is applicable to every type, but later we'll look at like the index checker, and some of those are only applicable to integers. Does that answer the question, Matthew?
Yeah.
Okay, cool. Bradley?
Does the framework assume single-threaded execution? I mean, for example, in that if statement example, at the time that the check runs, it could be non-null, and then some other thread makes this object null if it's shared state, and then the toString call would cause a null pointer exception?
That's a good question that I don't immediately know the answer to. Naturally, there's a lock tester, which sort of assumes that it'll be running that you sort of assume is going to be running in a concurrent environment. I don't know the details of the analysis. Oh, I see this because this is. I'm going to try to move that object to an instance variable and see what will happen. I might not know Java well enough to do this. Oh, I see. I have to annotate this. The details of when you can get away with not annotating null or not differ. So it looks like here it's going to do the check and then do the assignment, even though O might have changed by that point. Remember that here O is not a local variable. It's actually a dereference of the current object. So I'm guessing it assumes a single threaded execution here. That's an interesting detail about the checker framework. I didn't know though.
Thanks.
Yeah.
Other questions about what we've done so far? Okay, so the other thing that the checker framework will do for you is it will handle various sorts of operations. So each of the sort of fundamental statements of each of the fundamental statements in Java, it'll handle. It has rules for function calls, for assignments, and so on. So for example, to make this type check, I can call it with a valid value. And now the method is being called by something that is definitely not null. We're finding that out via refinement. And then I'm taking that result, which is nullable, and assigning it back to O, which is a nullable object, and that's valid. If I were to instead attempt to assign this to a not null object P, then I should expect to see some kind of issue. Oh, non-null object P, sorry. So now I'm getting an incompatibility. Bradley, and thanks by the way, Bradley, for posting that link in the.
Yeah, I just
Yeah.
wanted to say it's a command line option. You can toggle whether or not it assumes concurrency, and if it does, then it says it limits the amount of refinement it does.
That's cool. Yeah, the checker framework, if you investigate the manual, which I'm not going to make you all do, but is actually quite worth doing, you'll see that there's a lot of interesting, because it's actually used practically, there are a lot of interesting accommodations to it. So for example, there are all sorts of different command line options, and those command line options aren't always sound by default. So for example, if there are certain checks that you can turn on and off. This one seems to check if you declare an array and the type of elements of the array has to be non-null, then Java will fill them in with nulls by default, and you might not want that. There are checks that if something is known to be not null, checking whether it's equal to null is useless, so it'll complain about that. And there's also the possibility of turning off various checks. I don't see that in the manual like right here in front of me, but there are command line options to turn off checks. And some of the checks, even though they would be sound, are off by default because they generally give unhelpful error messages. So that's sort of a cool example of what it takes to actually make an analysis like this practically useful. Sometimes it involves some compromises on soundness, but on the other hand, the underlying analysis implemented here at least could be made sound, and attempts to take into account apparently even things like concurrency. Okay, so I've shown you the basics of the checker framework, how you add annotations, and I've even shown you that it correctly handles method calls and things like that. The other cool thing that is involved in the checker framework is, most of these checkers are actually have quite a bit of work put into them to make them not throw a lot of annoying error messages. And I want to demonstrate one version of that, which is also going to introduce a relational condition, which is one thing you often do in Java is you have some kind of map. So here I've defined a new map that maps strings to objects. And like any other programming language, you can write to the map and read from the map. So I can do map.put of hi, hello, and I can do map.get hi. So that's pretty much as you expect. Now, the way that map.get works is that it'll either return the value for that key or it will return null. So in particular, this is known to be an object, but it's not known to be a non-null object. Is it non-null or not null? Yeah, it's not known to be a non-null object. And you can see in the bottom left the error message, incompatible types in assignment. And that's because the checker framework has no way of knowing that hi is a valid key for this map. However, this you can imagine is going to be kind of annoying because often you will have some kind of method that, for example, receives a map and a key and wants to return the object at that key. And we'd like to annotate this method as non-null because we know that we will only ever call it with a key that is a valid key for that map. So we'd like to do something like this, but instead we find that there is an error. So, oh, sorry, I called it incorrectly. So instead we find that there is an error. When I call map.getKey, it returns a nullable object as opposed to a non-null object. So this is a situation that comes up pretty often because passing around dictionaries is, a reasonably common thing, and you will often know that some value is a key to that dictionary. So the checker framework also provides this annotation key4. And, I think you have to do this. Okay, I'm sorry. I'm gonna make a slight change to how I was gonna do this, just because my checker framework chops are not as good as I would like. So what I'm doing here is just moving that to an instance variable so that it can be referred to here. So what I've done here is I've applied the annotation key4 map, and this is another annotation added by the checker framework, something that is a key for some other value. And what goes here, by the way, is a general expression. So here I've named a field, but I can actually put an expression here, and the checker framework will parse it and track it. What the key4 annotation means is that this value is a valid key in this map. So you can now see that when I get the key from the map, because I've annotated it as a key for that map, the result is known not to be null. And the reason it's known not to be null is that implicitly when I wrote object here in the definition of map, I meant checker framework interpret that as non-null object. And so we know we'll get an object out, and as a result, it's valid to claim that we're returning a non-null object. Of course, if the map is allowed to contain null itself, then we will get additional errors. You've now seen the error pop up on that return statement, and that's because we might have a key that gets a value, but that value itself might be null. But let me get rid of that so I can continue demonstrating. So what we've now done, we've added the annotation key4, and that's allowed us to learn additional things about this map reference. But the next question is, how can we construct a value of key4? And the way you do that is by passing that value to map.put. So what I've done here is I've just taken the string hi, placed it in a variable k, and now initially that variable is not a key for anything, but after I call map.put, the checker framework applies something like actually the same technique as the refinement we discussed for learning from control flow tests. Now it does, it says that after a map.put, pretty much no matter what the answer is, I can now go backwards and refine the input expression k to know that it's a map for. So sorry, a key for. So now here I have, now it's valid to assign k to a key for, even though up here it would not be. So questions, Bradley?
So what if instead of map.put k, you wrote map.put k.reverse.reverse? Would that break it?
I sure hope reverse is how you reverse a string in Java. I don't actually ever program in Java, so it does not, right? And the reason for that is, let me see if I can actually. Oh, conveniently, actually, let me get my pen. I'll be right back, so that I can write on the screen for y'all. The reason is because what's going on internally to learn that k is a key for map is the same refinement process that we were talking about for conditional. So we have a call, map.put, and inside the analysis, it knows that k has the state, well, actually just non-null. And then the value we're putting, it also has the state non-null. And it calls a transfer function, which says that, in lieu of anything interesting, actually map.put returns void. So there's no annotations valid on void anyway. So this just returns, the transfer function tells us it returns top. But then, just in case, the checker framework also applies refinement. It asks the question in reverse. Suppose I know that map.put returned true. In that case, what do I learn about the arguments? Now, for most functions, this wouldn't be interesting, because the way we know that map.put returned true is because we just computed that. But for map.put, which mutates map, it is interesting because we can now go backwards and say, we've now additionally learned that this argument also has the annotation key for map. So that worked great when we just put a k as the first argument, because that now told us that k is a key for map. However, if instead we learn that about k.reverse.reverse, we now know that k.reverse.reverse is a key for map. But that doesn't tell us anything. If we now continue propagating it backwards, we know that k.reverse.reverse is a key for map. What do we know about k.reverse? Nothing particularly interesting at all. And then we take that nothing interesting at all, which here would, I guess, be non-null. And then we propagate that further backwards. If we know that k.reverse is non-null, what do we know about k? Just that it's non-null. And so this is an example where this analysis loses some precision because it doesn't have any special knowledge about k.reverse.reverse. Now, you could imagine if reasoning about string reversal was particularly important, that there might be some kind of at reversal of. So you could imagine some kind of annotation that would let you track that one string is the reversal of another, and then potentially you could sort of regain this information. If something is the reversal of something that is the reversal of k, then you would want that thing to acquire all the interesting facts that you knew about k itself. But that's not something that the checker framework analysis has built in. So right now, this k.reverse.reverse thing, it loses information because the information we want to track is reversal of. There's no way to state that in the checker framework itself. And so it fails to propagate the stuff it knows about k rev back to k. Any other questions? Or I guess a follow-up from Bradley if you want.
That was good, thanks.
Okay. Vlad? Any other questions about the nullness checker? Okay. Well, the nullness checker is in some sense the conceptually simplest of the checker framework checkers. At least on the outside, it looks like it just has two annotations, non-null and nullable. Even though, as you've seen, there's actually a few more. So we can tie this back to the stuff that we were talking about in class by drawing out that lattice. So remember, we had this idea that we could draw the lattices, and there would be this lattice. All in the lattice, we'd have all the different conditions that you can assign to a value, and the arrows between them would represent something that we derived from that OR rule, but specifically you can think of as implication. So we have, reverse implication. So here we have nullable values. Everything is nullable, including null. And then there's a more specific non-null value that is that we can apply to certain objects. And then the OR rule for these, of course, is that nullable or nullable is nullable, nullable or non-null is still nullable, but non-null or itself is non-null. And internally, the checker framework has various transfer functions that tell us things like, well, transfer functions that are applied in cases like, for example, method calls. And it also has refinement functions so that if you do a test of something with the literal null, then it'll also learn something interesting about that result. So questions about the nullness checker, how you might use it, and how it works internally. In that case, let me move on to demonstrating another checker built into the checker framework. And this one I'm calling the array checker, though I think in real life it's called index checker. So let me check that this is running. It is. Okay. So the index checker, or what I'll call it the index checker. The index checker inside the checker framework is meant for ensuring that you don't have array out of bounds errors. So to set this up, I've defined an index class here with a method that has two arguments. One is an array of strings, and the other is a single string, which we'll be using somewhat later for index of and similar. And so the first sort of thing that we can do, we can, since we're looking at array, indices, we can create some index and try to dereference an array in it. And after this runs, you will, that's not a statement. After it runs, we ought to get the error you can see at the bottom of the screen. Potentially unsafe array access. The constant index 2 could be larger than the array's bound. So this is sort of the fundamental thing that the index checker is trying to do. It is trying to check that the indices that you pass to arrays are valid indices for that array. And so the first thing that we can, the first thing that we want to do is I want to show you how you can actually create a valid index for an array. So here I just suggested that the array index should be 2. That's obviously not going to fly. However, if for whatever reason, we could instead declare this to be an index for C. And it's complaining about variable I not being initialized, which I guess is fair. If I were to move C to an instance variable, and then I could take an index for Ci as an argument. It's an index for C int I as an argument. This should type check. So this index for is the fundamental condition that we want to show about integers. But here, the way we haven't really established any way of establishing that condition. So first, let me show you one example of how you might establish it. I'm going to start by computing the length of C. And when I compute the length of a value, it is annotated with this conditional length of. Now, if I have some other integer, I can do Now, if I have some other integer, if I happen to know that that integer is in bounds and is bigger than or equal to 0 and it is less than the length, then the checker framework will internally refine the value of I to be an index for C. And that's using the basic logic that anything less than the length, bigger than or equal to 0, that's a valid index. So questions about this general setup of array bounds checking? I know that we've had it sort of as running example in class, so I wanted to show you that it's a real thing. Okay, so let's talk about the ways this will, let me show you how you'll normally use this. So far, I've had this sort of contrived thing where we explicitly test whether something is in bounds. But normally when you use an array, you'll use it in some kind of loop. So you'll do something like this. Something like C of I dot toString. So it seems to be the case that the checker framework has all figured this out. Let me try to make it a little easier to see what's going on internally. What we'd like to do is establish that I is an index for C. So our first idea might be to write something like this. But if we do this, you'll see that the checker framework actually complains about some stuff. And in particular, if I get the full output of that run, you'll see that it has two errors. One is it says incompatible types in assignment. And in particular, it's looking at the assignment of 0. In particular, it's looking at the assignment of 0 to something that is an index for C. That makes sense because we don't yet know that C's length is bigger than, or is that, sorry, we don't yet know that C has any elements. It might be a length 0 array. So 0 might not be a valid index for C. And the other problem it has is that we are incrementing I. And incrementing I internally, that means we're assigning I plus 1 to I. Well, if we add 1 to something that's an index for C, we don't necessarily get an index for C. So to help with this, the checker framework provides this alternative annotation, index or high. And now that I've done this, all the red squigglies seem to have gone away. So what index or high means is that C is an index, sorry, that I is an index for C, or it is one bigger than the biggest valid index for C. In other words, it is an index or the length of C. That makes this initial assignment valid because even if the array is empty, 0 is still the length of the array. So it's a valid assignment to index or high. That also makes the increment happy. Now, that part is a little subtler and has to do with this conditional. Remember that the increment only happens if the conditional returned true, if we went through the loop. When we do this test, we are comparing I to the length of C. And we find out that I is less. That allows us to refine I from index or high to just index 4. That allows us to enter this loop that shows that this array dereference is valid because we know that I is in fact less than C dot length. And this makes I++ valid. It takes something that is an index for C, it increments it by 1. So it adds 1, getting an index or high for C, and then it assigns it to a value of type index or high. And you can think of the annotation that I've inserted here for index or high. You can think of that as being an analog of the stuff you used to write in Daphne, which was like I is less than or equal to C dot length, even though in reality, in every iteration, it should be strictly less than C dot length. The cool thing, though, about using this finite set of conditions is that, as you see, and I didn't actually have to write this annotation explicitly. The checker framework somehow found it on its own. And the easy way to explain that is to say, well, think about it. There's only so and so many annotations we could have put on I. There's only so and so many variables in scope and so many different things I could write about it, index 4, index or high, etc. And so the checker framework does some kind of intelligent search to find the valid annotations that it could apply to try to make this stuff work. So questions about that? Okay. Okay, so far I've shown you annotations that we can apply to, array indices. There's also arrays that you can, annotations that you can apply to arrays themselves. So I might want to say that I have some array of, well, let's say integers, and I know for sure that 3 is a valid index of it. So let's do, so here's some statement I might write. This statement is a little confusing. This statement is a little confusing, but it is basically ensuring that we get the 3rd index of the array. And you can see that we get an error message here that 3 might be bigger than the valid indices to the array. And that actually makes a lot of sense because I've initialized D to be a length 0 array. However, if I were to instead initialize D to be an array of length 5, you'll see that that error goes away. So there must be something that the checker framework and that specifically the index checker is recording about the array D that allows it to learn that 3 is a valid index. And in fact, that annotation is called minlen. So here I've stated that maybe I don't quote it. There we go. Here I've stated that D is an array of length at least 5. The checker framework validates that because I've initialized it here to be an array of length exactly 5. And that allows us to learn that indexing it by 3 is valid. So what the checker framework is doing here internally is it is tracking these minlen annotations when possible on all the arrays that it has access to. And that allows it to check that certain annotations are valid. Similarly, let's move to another method. There are also annotations that combine 2 arrays. So let me have 2 arrays here and a method that attempts to dereference value of B. And let me just say that this is a index of B. It's not index of, it's index 4. Okay, so here I've just defined a method off to the side. I'm going to ignore the red squiggly here, which would require me to call this stuff. And here I get an index to the array A, to the array B, and dereference that array. Now, even if I have an index for B, even if I have an index for B, I can't use it to dereference from A and vice versa. So what I've done here is, this actually seems to work. Oh, sorry, it's getting hung up on. It was getting hung up on the actual Java type checker, not the checker framework. Now it's going through. So now I've declared that I is an index for A, but not that it is an index for B, and that is causing the checker framework here to say there's an unsafe array access. The index could be larger than the array's bounds. And the checker framework provides a relational annotation on arrays to allow us to handle this. So here I can say that the array B actually has to be the same length as the array A. And this actually still fails. I wonder if it only works in reverse. Huh. You know, I'm not totally sure how samenlen is supposed to work. Sorry about that. I did not plan that part of the thing. Okay. Well, there is a samenlen annotation, but unfortunately I cannot demo it. Sorry, guys. Okay, let me also show you some interesting ways that the index checker has been adapted to work with real Java code. So one of the simplest is to look at the index of method. So Java arrays have a method called index of. So I can do, and when I call index of, the way that the oh, is it like arrays.index of? If anyone wants to hint to me how index of works so that I don't have to embarrassingly look it up on the internet, you let me know. Yeah, array.index of should work fine. Not totally sure why it isn't working here. I guess while I'm trying to figure this out, if you all have any questions, please let me know. Okay, let me just take a, let me actually just do this, which I think will work. Okay, I don't know what happened with arrays, but the index checker works on general sequences. So I'll just switch to using strings for this. So here I've done index of for a string. I've received an integer back. And the way that Java specifies that is to say that the output is a valid index for F or for S, or it is the value -1 to tell me that the string was not found, the substring was not found. And in checker framework, I can explicitly use the annotation index or low to describe that. Oh no, that's right, strings are weird. Okay, hold on, there's something in the chat. Matthew in the chat suggests something like this will work, but it does not. Yeah, you know, I'm really lost on why this isn't working, but okay, fair enough. Okay. Thank you, all y'all Java programmers. Cool. So here I finally found something I can call index of. Thank you, William and Hao Chen on the. Thank you, William and Hao Chen in the chat. So I've created a list of strings. I've called index of on it, and that gives me a value of type index or low. And so what can you do with an index or low? Well, naturally you can say if k is bigger than or equal to 0, q dot what get, okay. There we go. So what we can do with an index or low is we can explicitly check, is it actually a valid index? And again, the checker framework here is applying a refinement to know that in this branch, it is actually index for q, k. So you can see this as a, you might not, if you were sitting down to think about array indexing in general, come up with this idea that index for or -1 is an important constraint to have. But it turns out to be a condition useful for analyzing a common pattern in Java libraries. And in fact, there's another common pattern that the checker framework index checker handles, and that is this idea that that the binary search method has in Java. So I think I tested this. There's a method in Java called arrays.binarySearch. And what arrays.binarySearch returns, you would think it would be like index of. It would return an index to the array or -1, but it actually does something a little weirder. And we can tell because if I say that J is an index or low, the checker framework will complain. So here it's saying incompatible types in assignment. And if I were to actually run this and get the full detail outputs, it tells us that the lower bound of J is unknown, lower bound unknown, but it's required to be greater than or equal to -1, which is incorrect. So why is that? That's because arrays.binarySearch has this weird API where it'll return an index to the array, or it'll return the negation of the index to the array. And it does that specifically in the case that the index is not found, in which case it'll tell you where it would go if you were to insert it. So there is a special search index of annotation in the checker framework. Come on. Search index 4. Thank you. There's a special search index 4 annotation in the checker framework, which captures this notion of being an index to an array or the negation of an index to an array. And actually, more specifically, it's the negation of the index -1. So again, this will work with refinements. So if I take J and I test whether or not it's bigger than or equal to 0, here I can assign it to an index for C. And that assignment will go through. Or naturally, I could use that to index into the array. So questions about the index checker? Okay, well, if you all have questions, you can always put your hand up and I'll try to get back to you as soon as I can. Also, the chat tips have been great. I want to show one last checker built into the checker framework, and then I'll show you the guts of a checker that I built myself. So this is a checker called the lock checker, and the annotation it provides is this thing called guarded by. So here you see that I've defined a class with a lock. I have a variable whose type is a lock. And then I have an object, which I said is guarded by that lock. So this goes back to Bradley's question of whether these @ things are refinements, as in do they restrict the set of values? And in this case, they don't. Every single object is a valid object to be guarded by the lock. Instead, what guarded by means is that reading from O, like calling toString on it, is invalid unless we also hold the lock stated. So you can see here, I've called O.toString and I've received an error message titled lock not held, required lock not held. So that tells us that if we want to actually read from the object, we must first do lock.lock. And once I've done that, then that red squiggly goes away because now that lock is held. So if I unlock the lock again, is it unlock or is it release? We will find out shortly. Oh, yeah, that's actually kind of interesting. So if we call unlock, you can see here that it is invalid now to call toString on the object, and that's again because the object says that it is guarded by the lock. The other interesting bit is that we now have an error message, and let me actually just make it bigger in this other window. We now have an error message that says releases no locks method test calls method unlock with a weaker may release lock side effect guarantee. And that's because if we want to track whether or not a lock is held when a method is called, we actually need to know effects of methods. Does a method release a lock or not? So here, by default, the annotation on this method in the checker framework is that it releases no locks, and method annotations are something that Java provides and the checker framework uses for effect things like this. So what I've implicitly done is written releases no locks test, and that's invalid because it does in fact release locks. I can write the much weaker may release locks annotation, and now you can see that the error message on unlock went away. But this also means that when we call test, the checker framework will now assume that locks might be unlocked. So if we have some other method where we call test, then it will basically clear the state of all the locks in play. And I think there's a way to also say which locks I might release. I suppose I could look that up in the manual, but I don't want to spend the time right now. Questions? The other interesting thing that goes on here is that when we call methods, we're going to want to know what the effects of those methods are. So you saw that here with may release locks. There's a couple of other annotations that you can provide. So let me actually call method and then call toString again. And the first annotation that you might write is that a method is locking free. Namely, it neither locks nor unlocks any locks. And that's actually trivially true of this method because it doesn't do anything at all. So you can see that here, after I call the method, it is still valid to call toString on the object because we in fact know that the method does not release any locks. Similarly, you can write a method that ensures that a lock is held. So here I'm going to write a method that will just go ahead and lock the lock. And I can annotate it with ensures lock held lock. That now allows, that is enough information to the checker framework that when I do that private method call to lock, the checker framework knows that, man, I should have named it something different. The lock called lock is now held, and so accessing this object is still valid. You can also write methods that require something to be held. So I can write a need lock method that, for example, calls toString on the object O. By default, this is invalid because the lock might not be held. But if I instead require that the lock is held before calling the method, then this red squiggle will go away. And it is correspondingly now not valid to call need lock here, but it is valid to call need lock here. So questions about the lock checker? Hopefully give you another example of, you might call this a relational condition, or you might even, I mean, in some sense, it's not really relational. It's more about, it's almost an annotation on nothing, just the program state itself, talking about which locks are held. So any questions? Okay, in that case, I wanted to show you the guts of what one of these checkers looks like internally. So I've actually written a little checker called div by zero. This is going off a lot of code that Mike Ernst, the creator of the checker framework, provided. So thank you to him. Here you've got the full source code, and you can ignore all the stuff with .class. If you're not familiar with Java, that's stuff generated by the Java compiler. So the goal of the div by zero checker is to check that you don't have any divisions by zero. And the way it does that is with a pretty honestly dumb hierarchy of conditions that looks like this. So it tracks positive values, non-negative values, and values in general. So the way that we do that is we start by defining some qualifiers. So you've got here top.java, positive.java, and non-negative.java, and those correspond to the @ things that I might be able to write, and also to this type hierarchy. So we can start with top.java. You can see that it is actually a class that contains no members at all. But it does have a lot of these meta annotations, which the checker framework uses for a lot of sort of magic by default. So you can see that I've annotated it as the default qualifier in the hierarchy. I've said that it is not a subtype of anything. I've said that it can be applied to integers, and that it in particular is going to be useful anytime we use a type, as in when we declare a type, or when we have a type parameter. So these annotations here are used internally by the Java compiler and the checker framework. The upshot of this is that anytime I have any kind of unknown integer, I by default say that it is a top integer, as in sign unknown, and that there isn't any, that isn't more specific than any particular thing. It's the least specific thing you could say. You can contrast this with non-negative.java. There's no more annotation of default qualifier and hierarchy because non-negative isn't the default. There are some things that aren't non-negative. Instead, I say that it's a subtype of top, and that defines this arrow here in the lattice. And then if we go into positive, we'll see something that looks quite similar, where it says that it is a subtype of non-negative. So far all that does is that defines the qualifiers, the ability to use positive, non-negative, etc. in Java code itself. And I have some Java code here that I wrote that uses those. So you can see that I've got a input integer that I've declared is non-negative. I have a non-negative integer whose value is 0, a positive integer whose value is 1, and then a bunch of arithmetic operations. After we've defined these qualifiers, we now need to make use of them. And in the checker framework, there's kind of 3 places where that comes up. First, you've got to decide how you apply those qualifiers to literals. So this happens in this crazy method called add computed type annotations. And remember that this is being run on the internals of the Java compiler, so some of the types here are a little bit crazy. But effectively, this add computed type annotations is being run on every expression in your source code. To do that, we first check, is that expression a literal? We ask, is that literal an integer literal in particular? We pull out the actual value of that integer literal. And now we say, if the integer is bigger than 0, we add the positive annotation. If it is equal to 0, we add the non-negative annotation. And otherwise, we don't do anything at all. And by default, the checker framework will add the top annotation. So questions about how I've set up this, this hierarchy and what I'm doing with literals so far? Okay. So far I've just defined the annotations that go on literals. The next thing that you probably want to do is you want to actually check whether divisions have the right annotation. And that happens in what the checker framework calls a visitor. So I've defined a visitor here. And the only method that's really doing anything in this code is this valid division operation. So you can see that because this is a visitor, and I know y'all have been working with visitors in some of your code, for the alternative assignment, it's got all these methods like visit compound assignment and visit binary. So we're overriding those methods. And in particular, what we're doing is when we visit a binary operator, we ask, is it actually an integer operator? And if so, we check whether that is a valid division. So inside valid division, what we're doing is we're checking, is this the kind of operation that we're interested in, namely a division or equal, sorry, a division equals, or a remainder equals. And if it is, we check that the right-hand side of the operator is annotated as a positive value. If it is not annotated as a positive value, then we return a string, and that string is later used by this visitor to call checker.report. And so that's actually the what you're seeing when I go into my example code here and I see an error on this division. You can see that at the bottom it says possible division by 0, and that's because inside it knows that z is annotated as non-negative, and here we have a division. So we find a division and we check the type of the right-hand side, and it does not have the annotation positive, so we throw an error. That's why this line throws an error, but this line does not. Questions? Okay, so I'm sort of running out of time. I didn't expect to spend quite as much time on some of the other checkers. But the other thing that goes on internally to the checker framework is transfer functions. So there's actually a lot of sort of boilerplate that goes on when you're doing transfer functions and refinements in the checker framework. So what I sort of want to tell you about this is that there are similarly visitors that run on every node in your program. And to make this stuff kind of digestible, I actually defined a helper class called Lattice to do all of the actual operations in. So for example, if we have an addition, which is done by visit numerical addition, what I'm actually doing is I'm calling the transfer plus method on the lattice object. And the lattice object, just to avoid dealing with all of the internal mechanics of the checker framework, is an enumeration that corresponds to the 3 classes we defined as qualifiers, and has methods like transfer plus that deal in terms of that enumeration. So transfer plus, for example, is what's called every time you have an addition. It takes in a left-hand side and a right-hand side, and it returns the annotation that you want to apply to the output. So here I've said that if the left-hand side is non-negative and the right-hand side is non-negative, then the result is non-negative as well. In fact, if you had a non-negative value to a positive value, then the result is positive, and otherwise the result is unknown. And that's what's going on under the hood here, where I say that 0 plus 0, well, that's going to trigger transfer plus with non-negative and non-negative. So that'll go down this branch, but it will not go down this branch. That'll return non-negative, and so we have 1 over non-negative. That's an error. But in this code, we have non-negative plus positive. That'll return positive here, and that will allow this division to work without an error. Questions? Okay, and then the final thing that we talked about in class that I wanted to demonstrate here is this idea of refinements. So here I have a little example of a refinement method called refine greater than. So refine greater than will be run every time you have a greater than comparison. And in particular, a greater than comparison set a control flow node, as in a conditional that is a greater than. So what is that doing? Well, refine greater than is run with a left-hand side and a right-hand side to the greater than comparison, and also a Boolean result. So that result will be true if the greater than returned true, false otherwise. And what it's returning is a new pair of annotations, an annotation on the left-hand side and the right-hand side in particular, that are additional information we've learned because we know the result of that Boolean. So for example, if we know that the greater than comparison returned true, and the right-hand side is non-negative or even positive, then we know that we have, for example, x greater than 0. If that's true, then we know that x itself must be positive. And so we have a refinement here. And actually, this refinement appears to be incorrect. I think it should be that, because we've now learned that the left-hand side is positive, but we don't additionally know that the right-hand side is positive as well. So good bug to fix. Meanwhile, we have this else branch, and that else branch is run when the result is false. So now we're looking at x greater than 0 being false, which you can think of as x less than or equal to 0, for example. So now we're looking at the left-hand side. And if the left-hand side was positive, we know that x is less than or equal to something. So we've learned something new about the right-hand side, which is that it must be positive as well. And similarly, the same for non-negative and so on. So that's how refinements work in the checker framework. And here you can see an example of that. If we change this to x greater than 0 and remove the annotation on x, you'll see that in this branch, we know that x is bigger than 0. It's positive, and so we actually know that this test succeeds. So I can divide by x safely. But in the other case, I don't know that that's true, and we still get an error. So for any further questions? Okay, I was hoping to demonstrate how to make changes to a framework like this as well. In particular, I wanted to add the ability to do something like if a negative value is not equal to 0, then it is positive. I'm not really going to be able to do that because we are out of time. But hopefully this demo has been useful to you nonetheless. If you wouldn't mind, please fill out the surveys that we have for class in general. I've already linked the feedback form here, and I should now also be making them due in Canvas, so they'll show up in your Canvas to-dos. So please fill that out, ideally right now. I've put the code for all of this on GitHub, and I will commit, actually let me just commit right now so that you know the results of class and you can see the code as it's been edited. So you can click that link on the course webpage to see all of the code that I demonstrated today. That's both the examples of using the different checkers and the checker that I wrote myself. And happy to take any other questions. And please use the feedback form to tell me how this demo format worked for you, because there's still time to avoid it for next class if you hated it. Yeah, if there's no further questions, you all are free to go. Okay, I am stopping the YouTube. Tenson, you are still connected, but if you have any questions to ask, please speak now. Otherwise, I'll sort of end the recording and the video. Okay.